Alright, so again, I'm just going to show you how I build a parallel circuit using the Multisim Live. So I'm going to start with the source and select the ground, and then I'm going to go to the power source and select a DC source. And now we're going to go and take the loads and use a resistor. Going to rotate it, and just going to copy it. And let's go with 3 again, and we'll go with the same values that we used earlier. Alright, so again, now just to connect it, alright, so again, just connect them. And so for the first one, let's use 1.5K, same as we used before. For the second one, let's use 220. And for the third one, we can use 680. And for our power source, we'll use 24 volts. So again, first step in the simulation is to select the components, put them on the page, then we go and change the values, then we're going to add the measurement instruments. So of course I'm going to add current here. First we have the total current, then I'm going to add the current measurement for each branch. So I need a current coming down here. Another one. And the last one here. Now I'll just add a voltage, because just so you can know that the voltage is going to be the same. So I'll put one on this side here. Alright, let's make sure we can see everything properly. May have to move the resistors up. Let's see if that helps. Alright, so I'll just bring this down a bit, just so that we can have more clarity. Alright, so now I can just hit run, and we should get all the values on the screen in a way that it doesn't block our component values. So now I can take this simulation and use it in the circuit. So now we have our circuit and we're good to go. Welcome to Prof. Scangrella. This time we're going to look at parallel circuits, and we'll take some time just to explain it and what you should look out for, and of course we'll try to work an example. Again, just a review as we get started. We have on the screen here some batteries in series and parallel. You can see again the series batteries. The voltage is going to add up, so our total voltage we expect to get here is 4.5 volts. Let's go here. So we expect to get 4.5 volts here. And of course, if each battery source is supplying 1 ampere, then we expect to get 1 ampere here. Right? Even though they're in series and each of them can supply 1 ampere, we will still get 1 ampere here. In this case here, with a parallel circuit here, our total voltage will be 1.5 volts. Right? Anything in parallel, the voltage will be the same. But the current will come from the source here, and the current will add up so that we will have a total of 3 amperes available to us. Right? Right? The current will add up here, and we'll have 3 amperes available for the parallel circuit. And you will see something similar as we look at our example today. All right, so again, if we have to put resistors in parallel with our source, again, we have, let's say if we started with a source here, if we had one load here, if we add another load in parallel with it, essentially that load will be drawing current from the source on its own. So in parallel, it's almost like the resistors or the loads act independently. Now, if you think of the home, although we have AC coming in the home, we have 115 volts. Everything you connect in your home, most of the items use 115 volts, and they're all connected in parallel. Each item is drawing its own current, and that is why you are advised not to plug too many items on one outlet, because each item you plug will be drawing additional current that can overload the outlet or overload the line that you're using. So how do we solve Ohm's law parallel problems? We use Ohm's law for each individual resistor, and the voltage source is always the supply right here. Right, so again, this will draw current and this will draw current, and so the total current is going to be the sum of all the currents that are drawn here, and that is called Kirchhoff's current law. That says that the current entering is going to be equal to the current leaving. Likewise, the currents entering here is going to be equal to the current leaving back here. Right, so this is what we will consider in the parallel circuit. Now let's start with a load here of, let's make this loads equal, right? Let's say this load is 10 ohms, and this one is 10 ohms, right? Initially, let me remove this one. So initially we have a 10 ohm load here, and so we can calculate our current, right? The total current according to Ohm's law is going to be equal to V over R, right? Which is 115 over 10, which gives us 11.5 amperes, right? So this is the current that is coming out of our power supply with just one load, right? And again, keep in mind for parallel, we said that each load is drawing its own current. So if you add another load on this same supply, and the load is 10 ohms again, guess what? So this is drawing 11.5 amps. This load will also draw 11.5 amps. And so now the total current that is coming from your power supply is going to be different, right? All right, so again, we apply Ohm's law here, and we find the current is going to be 15. Now we can see the total current, IT now, is going to be equal to I1 plus I2, which is going to be equal to 115 plus 115, 11.5 plus 11.5, which is going to be equal to 23. So we have 23 amps coming from our power supply. This is our total current. Now now our resistance will change, because our voltage is still 115, right? But our current moved from 11.5 to 23 amperes. So now you have to ask the question, what is the load that the power supply is seeing? So now we're applying Ohm's law from the perspective of the power supply, and we will see that this load is going to be equal to, according to Ohm's law, Vs over IT, the total current coming from the power supply. And so we can see that the load that the power supply is seeing is going to be 115 over 23, which gives us which is 5 ohms, right? And this is surprising, because here our load is, we have a resistor that's 10 ohms, right? And we have another resistor that's 10 ohms, but again, because both of these are getting current from the supply, right, we are now supplying double the current than if we had a 10 ohm resistor to the to the power supply. It appears that the load has been reduced, because keep in mind that with Ohm's law, the current is proportional to the voltage. So in this case here, since the current is changing and the voltage is staying the same, then of course the resistance must change, right? So the voltage is staying the same, the current changed. So now we have to calculate the resistance that the power supply is seeing. And so this is how we are able to estimate. Again, this system is used, we said, for all your home supplies. Everything is connected in parallel. And so since the more devices you connect, the more current you are going to use. And so since the voltage will stay fixed, when the current increases, the resistance comes down. And so that's the relationship that we have with Ohm's law. If the current is going to increase, the resistance will come down. If the resistance increases, the current comes down, and so forth. But in this case, every time you add a resistor in parallel, the current is going to increase, and so the resistance will come down. And this is what you will see. So in this case here, we see that the resistance has reduced, right? So there are a couple of things that we need to consider when we use parallel circuits. The first one being that the voltage across all the components in parallel is the same. So you can say same voltage across parallel. Okay, just a second. Same voltage across parallel loads. All right, the next thing we want to know is that the total current is going to be the sum of all the currents, and that is a law called Kirchhoff's current law. So IT is going to be equal to I1 plus I2 plus I3 ... All right, so the total current that comes out of the source is essentially based on the current of the individual loads. The other thing that we need to consider for parallel circuits is that of course, based on Ohm's law, we know that the larger the resistance, the smaller the current, and the smaller the resistance, the larger the current. The next thing we need to consider is also that to find the equivalent parallel resistance, there are two ways we can find it. We can find, so to find the resistance in parallel, we can use the product over sum, where we say R12 is equal to R1 times R2 over R1 plus R2. That's the product over the sum method. And then we also have the reciprocal method that says R12 is equal to 1 over R1 plus 1 over R2. This is where we find the conductances, and we take 1 over the conductances, and we have the resistance. Okay, let's look at an example. All right, so I have this example that I did in the simulation in the beginning. So you can see here we have 3 loads. Here, of course, the voltage is still 124 volts. You can see the maximum current that we expect based on simulation, and we can also see the current for each branch from the simulation, right? So also keep in mind that just to note, for the parallel circuit, the larger resistor will have the smallest current. So we expect our largest current to be with the smallest resistance, right? And we expect the smallest current to be here. And of course, based on the simulation results, you can see that right here. So the first thing we will do when we get this circuit, we want to find I1, I2, and I3. So let's find the total current. And then when we find I1, I2, and I3, we can find IT. So our I1 is going to be equal to, again, we can apply Ohm's law across this resistor. I1 is going to be equal to the voltage across this resistor, which is the same as the source. Again, the voltage is the same, VR1 over R1. So again, according to Ohm's law, current is voltage over resistance. And we have here 24 volts over 1500 ohms. All right, and that will give us 0.016 amperes, which is the same as 16 milliamps. Right? Then we go to I2. Our I2 is going to be equal, same thing, VR2. Now again, we said VR1 is the voltage across all the resistors are the same because they're in parallel. VR2 over R2, which is 24 over 220, which gives us, all right, 0.19, sorry, incorrect, 0.10909 amperes, which is the same as 109.09 milliamps. And for I3, same thing. I3 is VR3 over R3, which is equal to 24 volts over 680, which gives us 0.03529 amperes, which is the same as 45.294 milliamps. So if you wanted to find the total current, IT is going to be equal to I1, and this is Kirchhoff's current law, plus I2 plus I3, which gives us 16 milliamps plus 109.09 milliamps plus 45.294 milliamps, which gives us 160.39 milliamps. So right, we have our total current that is being drawn from our power supply, and we also have the current for each resistor. The next thing that normally you're asked to find is you're asked to find the resistance. What is the total resistance that the battery sees, right? We said that with each parallel resistance, the total resistance will reduce. So we need to find RT, right? So to find that, we can use Ohm's law. We can say that RT is Vs over IT. So this is an easy way to find the current, to find the resistance, which is going to give us 24 over 0.16039 amperes, and that gives us 149.63 ohms, right? This is the resistance that we get based on our current measurements. Now, the other ways we can find resistance, like we just said, there are two main ways. We can either use the product over the sum method, or we can use 1 over the reciprocal method, right? So let's go ahead and do the reciprocal method, right? So it's going to be 1 over 1500. So our RT is going to be 1 over 1500 plus 1 over 220 plus 1 over 680 and 1 over all of that. And that gives me, if I put this in my calculator, of course you should have a scientific calculator. All right, that gives me 149.64 ohms. So it's pretty close, right? All right, so now the next thing we need to talk about is power in parallel circuits. Of course, the power is similar to series circuits. We can find the power in each resistor, and then that will be we add this together, and that will be the total power for our circuit. So again, we can find PR1. Now there are different ways we can find the power. We can decide to say power is voltage times current, or we can decide to say power is voltage squared over resistance. And this is the more accurate way because we don't use any calculated values. It's going to be 24 times 24 over 1500, and that will be the power dissipated in the first resistor. And that gives me 0.384 watts, which is the same as 384 milliwatts, right? Likewise for power for R2, I can use V squared over R2, which is 24 times 24 over 220. And that gives me 2.618 watts. And for the 681, and so PR3 in the same method, V squared over R3, that will give me 0.847 watts. So again, the total power is going to be equal to P1 plus P2 plus P3, right? Which gives me 2.618 plus 0.847 plus 0.384. That gives me 3.849 watts, right? Again, if we wanted to calculate the total power, we don't have to go through this method. We can simply say that power is equal to voltage times current, and that will give us 24 times, and our total current we calculated was 160 or 0.16039, 0.16039. And that gives us the same answer, 3.849. All right, so this is how we calculate our total power. So again, now we have looked at parallel circuits. Again, just to reiterate, most times we calculate the current going for each branch first, and then we can find the total current, then we can find the total resistance. If we don't have the current, we can still find the resistance using just the resistors. And then we can also find the power as well. Again, we're saying with Kirchhoff's current law, the total current coming from the battery is going to be the current of each individual branch. So this is it for our parallel circuits here today. The clues that we mentioned, we have the same voltage across the loads, and so forth. So this is Prof. Scangrilla signing off. See you on the next one.